Let's continue our discussion of the first law of thermodynamics by introducing pressure-volume diagrams. So, a pressure-volume diagram is a good way of visualizing the way that the state of a system changes. Okay, and there are a number of ways that we can do this. The first, so let's look at an isochoric process, and that is when the gas has a constant volume. And so how does this system change? Well, here we have pressure on the vertical axis, the volume on the horizontal axis. Isochoric process is, I don't want to highlight, isochoric process is one that's just like this. So if it moves in this direction, we know that it starts at some initial pressure, and at a constant volume, that pressure increases. Okay? The next step is an isobaric process, so that's the gas is at a constant temperature, and that's this system right here. So we know, gas is a constant pressure, excuse me. So an isobaric process, we start at some initial pressure, the pressure does not change, and the volume will increase in this process. An isothermal process is when gas is at a constant temperature. So gas has a constant temperature, so a system that is just like this. Okay? And so we can see that the pressure and the volume will both change, but this is along what's called an isothermal curve. Okay, and so that means the temperature remains constant as the pressure and volume change within this system. Next we have an adiabatic change, which is very similar to an isothermal, with just a couple differences. So in an adiabatic process, no heat is transferred between the gas and the surroundings. Okay, so there's no transfer of heat whatsoever in this situation. Now, there's two main differences between an isothermal and adiabatic process. The first, and I will just annotate them quite quickly. The first difference is that an isothermal process takes place very slowly. So an isothermal process, there's a constant temperature, and the volume will change very slowly, and as it does, the pressure will change slowly. Whereas an adiabatic process, the change will place very quickly. So quickly, in fact, that there is no transfer of heat, which is what defines an adiabatic process. So it happens so quickly that no heat will be transferred in this process. Okay, and so the first difference is the time taken for these processes to occur. The second major difference is that an isothermal process, the gas is in equilibrium with the surroundings, whereas an adiabatic system process, it is not. And so an isothermal system, you could consider, say, some gas within a container, and this is thermally insulated from the outside world. So it's kept at a constant temperature. Let's say it's kept at a constant cool temperature. Okay, so no heat. So no external heat will come in or out. It's completely isolated from the outside world. Whereas in an adiabatic process, it is not. Okay, so it is not thermally insulated, and the external environment can affect what happens in an adiabatic process. Okay, and so the second difference has to do with the surroundings that each of these processes take place in. Okay, so we're going to come back to these and define these processes a bit more carefully using the first law of thermodynamics. And so the first law of thermodynamics is a statement of conservation of energy. Okay, so it's a way of saying how energy is conserved in a thermodynamic process. Okay, and so we can write it as delta Q is equal to delta U, so that's the change in heat. It's delta U, that's the internal energy, plus delta W, and that is the work that takes place. Okay, so we know that the change in a thermodynamic system, the change in heat is just the sum of the change of internal energy and the sum of the change in work. Okay, another way you can write this is just by rearranging the equation and putting it in terms of internal energy. So that's delta Q minus delta W. So the change in heat minus the change in work is the change in internal energy. Okay, so some heat comes into that system, and some of that heat is converted to work. Whatever is remaining gets converted to the internal energy of the gas within that system. Okay, so this kind of tells you the nature of the variables that define the state of define a thermodynamic system. So internal energy is, this is a state variable. Okay, so it can be defined by a set of known variables like pressure or temperature, or in this case, the heat and work done in a system. So it's defined by other variables, whereas heat and work are not state variables. Okay, so they both define changes in a system. What they do is they change the state of a system. They are not state variables themselves, but they will result in changes of state of the system. So changes of state is internal energy, pressure, volume, temperature, things like that. Okay, so just defining some conventions. So heat, if it's positive, then heat is absorbed by a gas. If heat is negative, then heat is lost by gas to the surroundings. Okay, so positive, it absorbs. Negative, it loses heat to the surroundings. And when it comes to work, if this is positive, that means it does work on its surroundings. And if it's negatives, the surroundings on its surroundings. And if it's negative, the surroundings do work on it. So work is done on the system. Okay, so let's look at some processes. Okay, so an isobaric process. So an isobaric process is one with a constant pressure. Okay, now if there's a constant pressure, first of all, we know that the work is just the area under this curve. Okay. And so that is a positive value. So let's go right here for positive. So that's a positive value. Okay, because the volume is increasing in this case. Okay, and we know that because of that, the temperature may also increase. And so internal energy will also increase, okay? And using the equation, Q will also increase. Because Q is work plus, if we remember the equation, delta Q is equal to delta work plus delta U. So if all these variables are positive, delta Q will also be positive. Okay, so in general, when looking at equations like this, it's important to know that a change in volume tells us if there's positive work done. Okay, so if the volume changes, work is done. And if there's a change in temperature, since temperature is related to the internal energy of a gas, then there's also going to be change done in the internal energy. Okay, so in an isobaric process, every single variable is positive. In an isochoric process is one where the volume increases. So let's look at a process where the volume is constant, but the pressure increases. Okay, so constant volume, the pressure increases. What is going to happen in this situation? Well, there's no change in volume. Okay, which means that I'll keep this black. So which means that there is no change in work done. Okay, because for work to be done, the volume of the system has to change. Okay, now if the pressure increases, okay, we know from the equation of state PV equals nRT. If P increases, the temperature must also increase. And what that means is that the internal energy must also increase. Because the internal energy increases, there is heat added to the system. And so both of these are positive. And if I did the reverse process, where I decrease the pressure, well, if you decrease the pressure, that means the temperature will decrease, and therefore the heat will increase. So it depends which direction we're moving in within this process, depending where we go. In an isothermal process. So an isothermal process, as a reminder, is one where the temperature remains constant. Okay, and so let's look at a situation like this. Okay, and so in this situation, it's an isothermal process. We know the temperature remains constant. And because the temperature remains constant, the internal energy will also remain constant. Okay, now we also know that because there is a change in volume, the work done will be positive. And based on the equation of the first law of thermodynamics, there's no change in internal energy, but there's a positive change in the work done. Therefore, there will be a positive change in the heat done. Okay, and so heat is added to this system, which creates an increase in the volume, and therefore the pressure decreases. Okay, and so these are some examples of how to use the first law of thermodynamics to consider what type of processes are being done, to consider whether it's positive or negative value. Okay, and for an adiabatic process, things may change again. So you can try that one on your own, how to find these changes in an adiabatic process. Okay, so that's a little bit about how to use the first law of thermodynamics.